Okay, so our team used multinomial naive Bayes to detect spam messages. So here's the learning task. So our task is to decide if the message is spam. So we got a Kaggle data set that contained a bunch of messages, each labeled with spam or ham meaning not spam. Um, and since this is a supervised learning, that means that our data had to be labeled. So um, that's what the spam and ham is for. And then this is also a classification decision task. So pretty much our model is going to need to make a score for ham, make a score for spam, and then decide which one is higher. And that is the decision that it makes. Moving
So
on.
once
Go ahead.
again, the model that we chose is the multinomial naive Bayes model. This model has the one distinct advantage of being dead simple to understand and implement. You'll see that in the code later. The basic equation is over there on the right side. Basically, we find the probability of each individual word in our message being spam and add all of those together, as well as adding the chance of it being spam at all. We do this process for both ham and spam data and then choose whichever one got the higher score. So, for example, with this test message, what is up, and this test data, all we have to do is cut the data in half. For the first word, count how many times it shows up, divide that by the total amount of words. Then we can just take the logarithm and do that for every word. Once we then add the probability of it being ham at all, we can do the math and get our ham score, which is negative 4.9 for this case. Once we do that for the spam table as well, we'll get negative 5.68. Negative 5.68 is a smaller number than negative 4.9, as we know, which means that according to our model, this message is a genuine human conversation. Probably. We'll get to the accuracy metrics later. Now, you might have noticed that I kind of lied. That wasn't the number of times the word appeared over the total number of words. We're adding other numbers to it. This is something called Laplace smoothing, and we have to do it because the model that we're using doesn't play very well with probabilities of zero. So we need to give every single word, even if it doesn't show up in the training data, some minimum amount that it can possibly be. And now it's time for the demo.
Cool. I will share my screen. All right. So now we're navigated to our Google Colab project, where I'll first talk about how we went about doing the data pre-processing process. So starting out, we installed any required dependencies slash libraries that we needed for our project, those being Kaggle Hub to help load the dataset, Pandas, NumPy, and map.plotlib to show any visuals. From there, we loaded the SMS spam collection dataset that we got from Kaggle into our Google Colab file here. And from there, we extracted only the first two columns that we wanted from interest and renaming them as label and message. The reason why we did this is because in the original data set that we got from Kaggle, there were originally like 5 columns, but the last 3 columns had unnecessary slash blank data that wasn't needed for our project here. From there, we converted the label column, which is the first column in this case, into numbers for easier modeling later on. Uh, and for that mapping, we did ham as 0 and spam as 1. We did this because in the original data set, the labels column, which is the first column, just had it as the string values. From there, we went on to actually clean each message using this clean text function. And the way we did this was first converting the whole message to lowercase, removing any punctuation, and then splitting the text into individual words into an array. And we applied this to every message that was in the second column. From there, we shuffled rows to remove any ordering bias. And then we had split the data into training and testing sets. We come to a consensus that the way we want to split this up was 80-20, 80% being training and 20% being testing data. From there, we separated the features and labels for each set. Um, so in total, we have over 4,000 entries as training samples and over 1,000 entries for testing. And these are some just examples of what each set has to offer. All right, now I'll pass it on to Aaron, where he will talk about the training model.
Yeah, so as Alex said, this model is very simple to implement. So all we really needed to do was count the number of spam, the number of ham, and also keep track of how many appearances each word makes in each class. From there, it was as simple as implementing the formula C plus alpha divided by N plus alpha V. Alpha in this case is 1 for Laplacian smoothing. Yeah, that's pretty much it. On to testing the model.
All right. So to test the model, we first started off by doing some Laplace smoothing, which just adjusts the denominators for the spam and the ham so that no word actually ever has like a zero probability. For the unseen words, it has a special like unknown bucket, and all like out of vocab tokens share the same probability. And we cap how many times this penalty can be applied so that gibberish, just like long strings of text, like don't overwhelm and tank the model. And prediction begins with the log priors for spam and ham, which reflect their overall frequencies in training. Then for each word in a message, we add its log probability if it's in the vocab, or fall back to the smooth value if not. And then finally, the model compares the total spam and ham scores. Whichever is higher decides on that. And that's how we tested it.
So I will share the other screen here. Okay.
Yep. And these are just some of the metrics that we had. So when we ran our test on it, uh, we had an accuracy of 97.94%. And some of these diagrams that we have over here, first, the confusion matrix. So there were 947 correctly recognized as ham, 145 correctly recognized as spam, 11 false positives, which are ham incorrectly flagged as spam, and then 12 false negatives, which is spam that slipped through as ham. For some of the other metrics, we have a precision, and this is out of all the emails we predicted as spam. The 145 were actually spam, and only 11 were mistakes. So when we call something spam, we're right about that percentage of the time. For recall, out of all the real spam emails, we correctly caught 145 and missed 12, which means that we're capturing about 92% of them. And then finally, we have an F1 score, and this balances both precision and recall, showing the model is not only strong at catching spam, but to also minimize false alarms. On the bottom, you can see the score distribution plot, which shows two mostly distinct groups, spam and ham, and the dashed line in the middle marks the decision boundary. And these are some good metrics because we want a high precision so that false positives or like putting a legit message as spam is super painful for users. We want a high recall because a false negative, which is like letting spam through, degrades inbox quality. And then as an F1 score, which combines both confirming the model can balance catching spam and avoiding false alarms. Comparing this model to the baseline model, if we were to predict everything as ham, which is the majority class, it yields about an 85.9% accuracy and catches 0% of spam. So our model of 97% accuracy is much better than that, and it's a strong improvement that actually is useful in practice. And what does this really say about the model? So with multinomial naive Bayes, we can see clear separation between spam and ham. The model remains conservative about calling something spam and only mislabeled 11 ham emails. Overall, these results indicate the model is accurate and reliable for real world spam filtering.
All right.